Okay, in this video, I want to talk about perhaps the most important thing you'll learn in this course, which is Newton's second law. More or less everything revolves around Newton's laws in this physics course. And part of the trick later on, when you start encountering what seem like new things, they're really just Newton's laws put into new forms. So later you'll encounter things like energy and momentum, but there's nothing really new. They're just clever new ways to frame Newton's laws. Newton's second law completes now the three laws of Newton. We're done with that, and we're ready to really start doing physics. Basically, Newton's second law says, well, okay, what if something is not at rest or moving with constant velocity? What's going on? What causes it to accelerate? How does its acceleration depend on its mass? What is a force? So we'll find out today what Newton's second law is. And so let's sort of review some of these concepts so we have sort of a big picture. So the first thing is, what is a force? And we've talked about it before, and I've sort of gone out of my way to use pounds in my examples rather than newtons, which is what we will essentially be using from now on. We're not going to use those pounds anymore, but the reason I did that is because you all have a good intuitive feeling for what a pound is. You don't have a good intuitive feeling yet for what a kilogram, I'm sorry, what a newton is. So we've talked about a force, and it's a push or a pull, but I want you to be sure that you understand that we haven't actually defined in any quantitative operational way what a force is, other than qualitatively it's a push or a pull. And apparently somebody or other defined what a pound was once, because you all sort of know what a push of 1 pound would feel like. And so, but really at this time, a force is not a fundamental quantity that we really know how to define it. What is a mass? Well, mass is well defined. Mass, let's talk a little bit about what mass is. The kind of mass we're talking about here is called inertial mass. Inertia, as you probably know, means that an object tends to keep doing what it's doing if no forces act. So it's basically Newton's first law, and therefore you will often see Newton's first law referred to as the law of inertia. The amount of mass that an object has is how much inertia it has. And what that means is, how hard is it to accelerate? So something real big, like a locomotive or a Mack truck, has a lot more inertia than something like a baseball. It's a whole lot easier for you to accelerate a baseball with a given force than to accelerate a truck with a given force. Mass, unlike force, is operationally defined at this point. It's defined to be a kilogram is the amount of mass that a certain chunk of iridium alloy in a vault in Paris has. This is of the three quantities which are sort of fundamental to our setting up physics: mass, length, and time. Mass is still not defined in a way that's really modern. They're the group of scientists who worry about those kinds of things are trying to come up with a better definition of a kilogram. But a kilogram is defined. Acceleration is also well defined because both the meter, which is a measure of length, and the second, which is a measure of time, are operationally defined. The second is based on an atomic clock, and the meter is essentially how far light will go in a vacuum in a second. No, that's not right. How many seconds it takes for an object to go 1 meter is specified. Okay, so now what we want to do in order to get a better handle on all this stuff is we want to do some kind of experiment. That's the way that we find out about nature, is by doing experiments. We want to do some kind of experiment to find out how the acceleration depends on what the mass is and how the acceleration depends on what the force is. So basically we're going to do an experiment with 3 different variables. One is the mass of an object that we're going to push or pull on. And the second, of course, is the force, if we're going to push or pull on it. And the third is what the acceleration is. Now you might say, well, how can we do that experiment if we don't know what a force is? So let's just say, okay, I don't know what a force is other than a push or a pull, but I can imagine making a machine which would always deliver the same amount of force. Every time I use that machine, it would push on it with some amount of force. I don't call it anything you like. Call it 1 Baker of force. Okay, so I make this machine, and every time I turn it on, it exerts the same force on whatever I'm pushing or pulling on with my machine. Now, if we want to find out how something depends on the force, we could just make 2 of those machines. In other words, we could imagine doubling the force or tripling the force and so forth. So even though we don't know precisely how to define force, we could certainly imagine a force that we could double or triple or quadruple in order to do an experiment to find out how things depend on force. Okay, so here's the experiment that I'm going to imagine doing. I'm going to imagine a mass sitting on a smooth surface. So here's my mass M. And I'm going to come with my machine, and I'm going to push on it with some force. Maybe that I will call 1 Baker. B is for Baker. Okay, and the result is that there will be some acceleration which I can measure. Okay, so I'll find out what the acceleration is if I take a 1 kilogram object and push on it with a force of 1 Baker, then I'm going to get some acceleration. And then the next thing I'm going to do is I'm going to, okay, so my first experiment, I'm going to keep this constant, but now I'm going to vary this. So then the next experiment that I do, I'll take a 2 kilogram mass, okay, push on it with a force of 1 Baker, okay, and again measure. We'll call this guy up here A1, we'll call this guy A2, so now we'll measure A2, and then we'll do it for 3. We'll still push with the force of 1 Baker, okay, and now there'll be some different acceleration and so forth. And then what I'm going to do is I'm going to plot the results. So let's just see if we plot the mass as a function of, plot the acceleration as a function of the mass. What do we get? Well, let's think about it a minute. Suppose the mass is extremely large, okay, way out here beyond 6, okay? Well, then I'm going to get a very small acceleration. Suppose the mass is very small, somewhere around here, okay? Then I'm going to get a very large acceleration, okay? And so now I'd make a bunch more points like this, and what I get is I get a bunch of data points which would fall like this. Okay, in other words, I would get a curve that looked like that. Okay, so if I keep the force constant, vary the mass, and measure the acceleration, I get a curve that's something like this. Well, that curve obviously tells me something I want. However, it really is not terribly helpful because we always like to get a straight line. It's nowadays, of course, computers can go ahead and you can take these data and you could tell it to fit to some curve or other. But of course, Newton didn't have any computers to do curve fitting to data. And so he had to be more clever than that. And this is actually one of the nicest tricks that physicists use all the time. Okay, they get some sort of curve or other, and they look, if they possibly can, if they can find some way to turn it into a straight line. Because if it's a straight line, then we can say for sure how one of these variables depends on the other. So, for example, we might say that suppose instead of plotting the acceleration as a function of the mass, suppose we plot it as a function of the mass squared. Or suppose we plot the acceleration as a function of 1 over the square root of the mass. And so, or maybe suppose that we say that we will plot it as a function of the mass to the 2/3 power, and so forth, okay? Keep fiddling around. Of course, I sort of do this naively, trying to make you understand that we have to fiddle around a bit. But in fact, you might say, well, what's the easiest thing I might choose? And the easiest thing I might choose to do is plot the acceleration as a function of 1 over the mass, okay? Because that would be the most logical thing to do. So let's suppose that we do that. Okay, so now I'm going to take that same data. Okay, now the data when I plotted the acceleration as a function of mass, when we went to very, very large data, or very, very large mass, okay, we found very, very small acceleration. And in fact, if we had gone to infinite mass, we would have found 0 acceleration. Okay, and so we get 1 point here, gratis. Okay. And next we say, well, okay, suppose now I come to some other point which has still a very large mass, okay, then maybe I'd get a point here. And now as I keep going to bigger and bigger masses, I'm sorry, going to smaller and smaller masses, I go to bigger and bigger accelerations. And if I take those data that were on the previous page, remind you, those guys look like this. If I take those data and plot them now, lo and behold, I get a beautiful straight line. Okay, and no matter how carefully you take your data, you'll never find any change away from a straight line. Okay, so our experiment is half over. We have found that the acceleration is proportional to 1 over the mass. Or, the way they often say it in a math class, the acceleration is inversely proportional to the mass. Okay? So that's the first part of Newton's second law. So let us now proceed. Okay? The next thing we want to do is keep the mass constant and change the force. Okay, so maybe I should go back to this page and sort of be sure that I understand what I'm doing now. Okay, so now what I'm going to do is I'm going to do a similar experiment, except that now I'm going to keep the mass constant. Okay, so we keep the mass constant to 1 kilogram or 3 kilograms or whatever you like. So then I'm going to push with a force of 1 Baker. And I will get some acceleration, a sub 1. And then I'm going to take 2 of my machines, and now I'm going to put 2 Bakers of force on this same mass, and I'll get some different acceleration, A2. And again, I'll keep the mass constant. Now I'll take 3 of my machines so that I'm exerting a force of 3 bakers, and now I'll get some acceleration A3, and so on until I have enough data that I'm happy with my results. So if I now go down here and start plotting these results, I say, well, first of all, if I don't push at all, okay, then the acceleration will be 0. So I get this point gratis from Newton's first law. Okay, so this point here now represents Newton's first law. If the force is 0, the acceleration is 0. And now what I find is that if I exert a force of 1 baker, then I get an acceleration of ½ meter per second. 2 bakers, 1, and on and on and on. In other words, I get a straight line. So now I get that the force is proportional. Sorry, that's not what I want. I want to say that the acceleration is proportional to the force. So if I push twice as hard, I get twice the acceleration. If I push 10 times as hard, I get 10 times the acceleration. If I have a mass and I double it, I get half the acceleration. If I make it 10 times bigger, I get 1/10 the acceleration, and so forth. So, what have I found? I've found that the acceleration is proportional to the force, and the acceleration is proportional to 1 over the mass. And so finally, I find that the acceleration is proportional to the force over the mass. That is what I call Newton's second law, because it tells me how nature behaves. I like to think of laws in terms of proportionalities. This tells me that the acceleration is proportional to how hard I push and inversely proportional to what the mass is. Okay? Now, we don't really like to work with the proportionalities. We'd rather work with an equation. So in order to turn a proportionality into an equation, all you have to do is introduce what's called a proportionality constant. So C is some constant divided times F over M. Okay? Now, the question becomes, what is the proportionality constant? Well, there are 2 possibilities. First of all, if you already know what you mean by acceleration, what you mean by force, and what you mean by mass, then you have to go to a laboratory and measure what that proportionality constant is. In essence, that was sort of like when we were talking about friction, we had to go to a laboratory and measure what the coefficient of friction for steel sliding on wood is, or something like that, because there was nothing in that equation that we didn't know what it was. But now, and the reason I emphasize this at the beginning of this video, there is something in this equation which is not well defined yet, and that is F. Okay, so I emphasized at the beginning that force is not well defined, and so we can use the choice of the proportionality constant to define what a unit of force is. So for example, in other words, I can choose the constant C to be anything I want. I could choose C to be 7. Okay, so suppose that C was equal to 7. That would tell me that Newton's second law now could be written as CF over M is equal to acceleration, which is equal to 1/7. Oops, sorry. That is equal to 7F over M. Okay, so suppose that M equals 1 kilogram and A equals 1 meter per second squared, then the force would be equal to 1/7 units of force. Well, does that make sense? Well, basically what it says is that if F is equal to 1/7 of a unit of force, for example, 7 might define what a Baker of force was, okay, that would mean that if you applied 1 unit of force, you would get an acceleration of a 1 kilogram object. Okay, let me write this down a little more carefully. Okay, so our new Newton's second law is that F equals 1/7 ma. Okay, so that says that if F equals 1 unit, okay, then acceleration is equal to 7 meters per second squared if m equals 1 kilogram. So 1 Baker of force would cause a 1 kilogram object to have an acceleration of 7 meters per second squared. Well, I would say that would be a pretty dumb way to say what a force is, to define a unit of force. So I'm going to choose a number that I like much better for C. C equals 1, F equals ma. That's Newton's second law. And what a unit of force is if you exert 1 unit of force on a 1 kilogram object, it has an acceleration of 1 meter per second squared. Okay, and 1 Newton is equal to 1 kilogram meter per second squared. That's what a Newton is. It's that force which, if you exert it on a 1 kilogram object, the object has a speed, acceleration of 1 meter per second squared. Okay, this video has probably gone on long enough. One final review. Newton's second law is 2 things. It's a statement of an experimental fact, and it's a definition of what 1 unit of force, called a Newton, is.